Now we move into telescopes, the tools that let astronomers actually get the light from the universe. So our eyes are powerful, but they are limited. So to explore space, astronomers need something much better. And the main reason we need telescope is that most cosmic objects are faint. Our eyes just don't gather enough light. So think of a telescope as a giant light bucket. The bigger the bucket, the more photons or light particles it can catch. And more photons mean we can see faint and farther objects. Now, to do this well, telescopes have to be both large and extremely precise. The mirror has to be polished smoother than a human hair, and the entire structure has to stay stable. Even small vibrations, temperature changes, or any misalignments can ruin an image. And the bigger the telescope, the fainter the objects we can detect. So, with telescopes, astronomers can observe galaxies billions of light years away, watch planets orbiting other stars, and see details our eyes could never reveal. Now, here's a great example. This is the Gemini North Telescope in Hawaii. You are looking at it with a fisheye lens, which makes the dome look curved and dramatic. And that big dome is not just for looks. It shields the telescope from wind and helps control the temperature inside, so the air doesn't shimmer and blur the image. So inside sits an 8-meter mirror, about the size of a classroom, collecting light from across the cosmos. So telescopes let us go far beyond what our eyes can see by gathering more light and keeping it steady. Alright, now that we know why telescopes are essential, let's explore the two main designs astronomers use to focus that light. So how do telescopes actually work? Their main job is to take light from space and focus it into a sharp image that we can study. So without this focusing step, the light would just scatter and we would see nothing useful. Now one way to focus light is refraction, bending light as it passes through a glass lens. And Galileo's famous telescope in 1610 used this method. So imagine sunlight passing through a magnifying glass. It bends the rays and brings them to a point. And that's exactly what a refracting telescope does, but with distance starlight. Now, have you ever seen how a straw in a glass of water looks bent? And that's refraction at work. So, refracting telescopes use that same bending principle, just with big, carefully polished lenses. And the second way is reflection. That means bouncing light off a curved mirror. And Newton built the first reflecting telescope because lenses had problems. Large glass lenses were heavy, hard to polish, and created weird rainbow colors around objects called chromatic aberration. But a mirror avoids all that. It reflects light instead of bending it. And you can support a mirror's back so it won't sag like a giant lens would. Now think of how you see yourself in a curved bathroom mirror. Your image gets focused and sometimes magnified. So reflecting telescopes uses the same principle but on a huge scale. So whether you use a lens or a mirror, the goal is the same. Bring light rays together at a focus point. And once the light is focused, an eyepiece or a camera magnifies the image so astronomers can study it. Alright, now that we know the two basic methods of focusing light, bending with lenses or bouncing with mirrors, let's compare refractors and reflectors in more detail and see why modern observatories prefer one design over the other. So now each telescope type has its strengths and weakness. And history shows us how astronomers moved from one to the other. So, a refractor uses a big curved glass lens to bend light and bring it to a focus. And that's what Galileo used when he first pointed a telescope at the sky. But refractors come with a major issue, which we call as chromatic aberration. That means different colors of light bend differently, just like when sunlight passes through a prism and splits into rainbow. And that means a star might look sharp in one color but blurry in another, with colored fringes around it. So think of when you have seen rainbow colors along the edge of eyeglass or camera lenses. And that's chromatic aberration in action. Now on top of that, large lenses are very heavy, expensive, and can only be supported at the edges. So imagine holding a giant dinner plate only by the rim. It starts to sag. So that's the problem with very large lenses. And fortunately, reflectors solve these issues. Instead of bending light, they bounce it off a curved mirror. So mirrors don't separate colors. So there's no chromatic aberration. And unlike lenses, mirrors can be supported from the back, which makes them much easier to build in large sizes. And that's why almost all modern research telescopes, including the world's largest, are reflectors. So think of your bathroom mirror again. No matter what color your shirt is, the mirror reflects all colors equally. And that's why reflectors don't get rainbow fringes. Now Galileo's refractor opened the door to astronomy. He discovered the moons of Jupiter with it. But Newton's reflector in the 1600s became the blueprint for the modern telescope. And today, when you hear about huge observatories like Gemini or the James Webb Space Telescope, those are reflectors, not refractors. Now here's a simple comparison. On the left, the refractor uses a lens in the front to bend light, and on the right, the reflector uses a mirror at the back to bounce light to a focus point. Now notice how the designs look different, but both aim to do the same thing, concentrate light into a sharp image. So refractors were the pioneers, but reflectors become the workhorses of modern astronomy. Now we just saw how refractors bend light through lenses and reflectors bounce light off mirrors. So one big reason reflectors became dominant is a problem that affects all refractors, chromatic aberration. Remember? So what is it? Now chromatic aberration happens because different colors of light bend by different amounts when passing through a lens. So blue light bends more than red light. So the colors don't meet at the same focus point. There are different focus points. So see, this image shows this clearly. Blue, yellow and red components are focused at slightly different points, creating a rainbow blur around the star. So this makes it hard to see sharp details. And that's why early refracting telescopes often showed stars with tiny rainbow halos around them. And that made it hard to see fine details and frustrated astronomers who wanted crisp images. Now to reduce this problem, telescope makers developed chromatic lenses, which combine two types of glasses to bring two colors, usually red and blue, into focus together. So in this figure you can see that the rainbow halo is largely gone. That means this reduces the color fringes dramatically, but it's still not perfect. Other wavelengths are slightly out of focus. So while achromatic lenses improved refractors, they couldn't completely eliminate chromatic aberration. So because of chromatic aberration, refractors became less practical for very large telescopes, and astronomers started turning to reflectors, which don't have this problem. Now I know some of this might sound familiar because we just talked about reflectors and why they dominate modern telescopes. But this slide highlights real examples of today's largest optical and radio telescopes, which really helps put things in perspective. So just to recap, reflecting telescopes are easier to build large, avoid chromatic aberration, and can be supported from the back. And these are the main reasons almost all modern telescopes, optical or radio, are reflectors. So here's an example. The Gemini North Telescope in Hawaii. It has an 8.1 meter mirror, which is bigger than most classrooms. And its dome is designed to reduce turbulence and keep the temperature stable so the mirror can collect light precisely. So with this telescope, astronomers can see extremely faint and distant objects in the universe. And reflectors are not just for visible light. Radio telescopes also use mirrors in the form of giant dish antennas. For example, the Green Bank Telescope in West Virginia is essentially a huge satellite dish. So look at the size. It's big enough to hold a football field. Even though it doesn't look like a traditional telescope, it's using the same principle, reflecting waves to a single focus point. So radio telescopes collect radio waves from space, which are much weaker than visible light. So the huge surface area is necessary. Alright, next we will move on to what telescopes can actually do. Their powers like light gathering ability, resolution and magnification. Okay, now let's talk about what really defines a telescope's strength. So astronomers describe this using three powers: light gathering, resolving and magnifying. So you might think magnification is the most important, but surprisingly, it's actually the least important. It doesn't help if the image is blurry or faint. So first let's talk about light gathering power, or we call it LGP. So this depends on the size of the telescope's primary mirror or lens. So think of it like a bucket catching rain. The bigger the bucket, the more water it collects. So a bigger mirror collects more photons, letting us see faint stars, galaxies or nebula. And the area of the circular mirror increases as the square of its diameter. So even small increases in size give huge gains in light collection. Now how do we calculate the area of the primary lens? So the formula for area is A equals phi d square over 4. So how do we get this equation? D is the diameter of the mirror. So what is the radius? Radius is just d over 2. Therefore area is just the area of a circle. That means 5r square, 5 d square over 4. That's the area. So therefore the LGP or light gathering power ratio between two telescopes is just the square of the ratio of their diameters, which is LGP A over LGBP equals to square of dA over dB. Alright, now look at this figure. The small telescopes collects only a little light, while the large telescopes act like a bigger bucket, catching much more. And that's why large observatories like Gemini or Keck can see extremely faint and distant objects. Now the next parameter is resolving power, the ability to see fine details. So even with enough light, a blurry telescope can't separate objects that are closer together. So for example, two stars that appear as one blur in a small telescope can be clearly distinguished with a larger telescope. So resolving power depends on the diameter of the mirror. That means bigger mirrors improve resolution. And finally magnifying power. And this enlarges the image. So many people think this is the most important, but it's actually the least critical. Magnification doesn't help if the image is too faint or blurry. it just stretches the imperfections. So astronomers focus first on collecting light and resolve in detail, then apply magnification as needed. Okay, now that we understand the three powers of a telescope and why size is so crucial for light gathering, let's see an example comparing telescopes of different sizes and how much difference that makes in practice. So let's apply the light gathering formula we just learned. So this shows why even a moderate increase in telescope size makes a huge difference in how much light we collect. So in this question, we are asked to compare a 24 centimeter telescope with a 4 centimeter telescope. Now before I solve it, you can pause the video and give it a try. Alright, now we know the diameter of each telescope, right? Diameter of the 24 centimeter telescope, which is 24 centimeter, and the diameter of 4 centimeter telescope is just 4 centimeter. So let's apply our equation. LGB 24 telescope over LGB 4 telescope equals to D24 over D4 square, right? Diameter of each telescopes. So we know the values. So let's plug in the numbers. Diameter D24 is just 24 centimeter and the other one is 4 centimeter. So after calculating, when we get the square of the ratio, we get 36. So what does that mean? That means the 24 centimeter telescope collects 36 times more light than the 4 centimeter telescope. So imagine trying to see a faint star. The larger telescope acts like a much larger bucket, gathering far more photons, which makes faint objects visible. Alright, now that we understand how telescope size affects light gathering, let's move on to resolving power, which is the telescope's ability to distinguish fine details in the sky. Now resolving power. So what is it? We briefly discussed about it in a previous slide. Remember? It's the telescope's ability to see fine details clearly. Even if a telescope collects a lot of light, it will not help if two close objects blur together. Now resolving power is measured as the smallest angle between 2 points that a telescope can still see as separate. And this is limited by diffraction, which describes how light waves spread slightly when they pass through an aperture. So when we focus an image, instead of a point, we get fringes around it. That is due to diffraction. So here's the formula for resolving power. Theta equals 2.5 times 10 to the power 5 lambda over d. And here lambda is the wavelength of light and d is the diameter of the telescope. So this means larger d gives a smaller theta, meaning finer details. So when theta is smaller, we can get finer details. So we can resolve objects more closer together. So again, a smaller angle theta means sharper images. So larger telescope resolve finer detail and they can separate two stars that would look like one blur in a smaller telescope. So larger telescope resolve finer details and they can separate two stars that would look like one blur in a smaller telescope. Okay, let's look at this figure. Even though stars are extremely far away and should appear as perfect points, light behaves like a wave. So this causes each star's image to be surrounded by diffraction fringes, as I said before. Instead of one point, we get fringes around the point. Now as in figure B, when two stars are very close together, then their diffraction patterns overlap, making it impossible for the telescope to distinguish them as separate points. So this illustrates the limit of resolving power. If the angle between stars is smaller, then the telescope resolution is worse. Then they appear as a single blurred object. Alright, now that we understand resolving power, let's work through an example to see how it applies to real telescopes and star separations. Alright, so let's calculate the resolving power for a real telescope. So in this case, 5-meter optical telescope observing green light at 550 nanometers. So D is 5 meter and wavelength is lambda is 550 nanometer. Now before I solve it, can you try to get an answer? Pause the video and apply the equation for resolving power. So now we know the diameter of the telescope, which is 5 meter, and the wavelength of light, which is 550 nanometer. So notice here the wavelength is in nanometer and we have to convert it into meter so that we get the final unit in arc seconds. So meter unit will cancel out. Because D is in meter, so lambda should be in meter, so meter unit will cancel out and we get the final unit in arc second. Okay, so we can do that by multiplying 550 by 10 to the power minus 9 because nano is 10 to the power minus 9 meter. So 550 times 10 to the power minus 9 meter, which gives you 5.5 times 10 to the power minus 7 meter. So always check units before plugging into formulas. Alright, so let's plug in these values to our equation. Lambda is 5.5 times 10 to the power minus 7 meter and D is 5 meter. So if you solve for this, you should get theta equals to 0.028 arc seconds or roughly 0.03 arc seconds. And that is incredibly sharp, far better than the human eye, which can only resolve about 60 arc seconds. And this is 0.03 arc seconds. So this shows the power of a large telescope in distinguishing extremely fine details in the sky. So of course, in practice, Earth's atmosphere blurs images. So even a perfect 5-meter telescope doesn't always reach this resolution. Alright, so let's discuss atmospheric effects and adaptive optics that astronomers use to overcome this limitation. Now in reality, Earth's atmosphere often ruins the resolution advantage of even the largest ground-based telescopes. Now you may have noticed that stars twinkle at night, right? And that twinkling is actually the air bend in the light, which also blurs telescope images. So think about this. If a telescope can theoretically resolve 0.03 arc seconds, but the atmosphere blurs it to 1 arc second, so then what happens to the detail you can see? So this blurring effect is called seeing. So typical ground-based seeing ranges from 0.5 to 5 arc seconds. So the atmosphere limits the telescope's resolution. So even a huge telescope cannot always reach its theoretical sharpness. Now to counteract this, telescopes use adaptive optics. So lasers create artificial reference stars and deformable mirrors adjust in real time to cancel turbulence. And alternatively, we can avoid the atmosphere entirely by putting telescope in space. Simple as that. The Hubble Space Telescope does this, producing extremely sharp images without atmospheric distortion. So look at this image. On the left, star appears smeared into a blob because of atmospheric turbulence. But on the right, adaptive optics restores sharp details. So take a moment to notice the difference. Now even though the atmosphere limits telescope on Earth, we have clever technologies to overcome it now. Alright, the last telescope power we will cover is magnification. How big the image appears. So many people think this is the most important feature, as I said before. but surprisingly, it's actually less critical than light gathering or resolution. So, what is magnification? Magnification is given by the formula m equals fp over fe. Now here f means focal length. So what is focal length? If you have a lens or mirror here, when light comes through the lens or the mirror, then it focuses it into a point, and we call this distance focal length f. And here fp is the focal length of the telescope's primary lens or mirror. That means the distance over which it focuses light to form a real image. And fe is the focal length of the eyepiece, which magnifies that image for our eyes. So the magnification is simply the ratio of these two focal lengths. So the objective lens or mirror collects light and forms the image, and the eyepiece magnifies that image. So change in the eyepiece changes the magnification. That means you can change magnification by swapping eyepieces. Short eyepiece focal length gives higher magnification. Now remember, if you make the image bigger but the telescope doesn't gather enough light or resolve details, then what happens? Then the image just becomes larger and blurrier. So magnification is limited by the telescope's resolving power and light gathering ability, which we discussed before. And high magnification alone will not reveal more detail. So the telescope must first be able to clearly resolve and collect enough light from the object. Okay, let's do a quick magnification example so you can see how to apply the formula step by step. So this will show how easy it is to calculate and what it means in practice. So before I show the solution, you can pause the video and try this yourself. So the formula for magnification is fp over fe, right? And fp is the focal length of the telescope's primary lens or mirror, and fe is the focal length of eyepiece that magnifies the image. Now for our telescope, fp is 200 cm and fe is 2 cm. So let's plug in these values to our equation. M equals 200 divided by 2, which gives 100. So this means the telescope magnifies objects 100 times, right? If this length is L, then we get 100 L, bigger image. But remember, magnification only makes the image larger. But if the image is faint or blurry, increase in magnification will not help. So think about why light gathering and resolving power are still essential. Okay? Alright, now we have finished all three telescope powers: light gathering, resolving and magnification. So let's wrap up and see how they work together. Light gathering power, it is the most important power. It determines how faint an object a telescope can detect. Remember, bigger mirrors or lenses collect more light, like a bigger bucket catching more rain. Next one is resolving power, which tells us how fine the detail is. Even a larger telescope can't always reach its theoretical resolution. Why? Because Earth's atmosphere blurs images. But adaptive optics or space telescopes can overcome this limitation. And finally, magnification is the least important. So without enough light or resolution, high magnification just makes the image bigger and blurrier. So always prioritize light gathering and resolving power first. So that concludes section 2, telescope powers. So now you are ready to move on to non-visible astronomy, including radio and space-based telescopes, which reveal parts of the universe we can't see with our eyes.